Right. Analytical chemistry, we just completed mass spectroscopy in the previous lesson. I hope you remember all the methods of reading the spectrometry, the difference between the spectrometry and spectroscopy as well. Spectrometry does not involve the interaction of electromagnetic radiation with matter, whereas spectroscopy does involve interaction of the electromagnetic radiation EMR with matter. That's the difference between the spectroscopy and spectrometry. The last few questions, I hope you have tried them, especially the question on the page number 8. These 4 questions. Today we'll begin the study of the spectroscopy. Now, as I mentioned last week, spectroscopy involves the interaction of the electromagnetic radiation with matter. So here we have different types of spectrophotometric techniques, but here we'll be studying mainly about the IR spectroscopy. You have NMR spectroscopy, H1 NMR, C13 NMR, all those will be done on the A2. In AS, we have one spectroscopy technique, which is IR, where we study how when infrared radiation, in short we say IR, infrared, infra in Latin means next, or next. Infra means next to red. Next, infra is next, so next to red is infrared. That means next to the red color of the spectrum, the visible range, the red color is there. You have the, if you remember the electromagnetic radiation, you have the visible light in the center, and you have in the higher frequency side, you have the X-rays, UV rays, X-rays, and gamma rays, and you have on the low frequency side infrared, then microwaves and the radio waves, right? So here we study how when infrared radiation interacts with matter, how various observations, based on the various observations and various absorptions, we conclude the presence of various groups in the molecule, right? So before I start explaining the spectrum, how to read a spectrum, let me first explain what a chemical bond is and how a chemical bond, how a chemical bond acts as a spring, right? Now, if you take a bond, any bond, when I say any bond, I'm referring to the covalent bonds here, not ionic bonds. Which we study about organic molecules and the infrared spectrum. So when it comes to covalent molecules, right, you have the nucleus, right, and then this is 2 nuclei, and this is a shared electron pair. What happens? This shared electron pair will get attracted towards the nucleus, right? Get attracted towards the nucleus. When they come very close, like this, what happens? The nuclei repel. Nuclei repel, right? So this is the nature of the bond. It's always like this. It's like they come closer together towards a shared electron pair, and they repel away when the nuclei are very close. The 2 positive charges of the nuclei, they repel again. Then when they go away, far away, then they come together again. So it's like a spring. So you have the 2 atoms, right, like this. This is another atom, another atom. So it's like a spring. So they come closer, and then they again move apart, and they come closer, move apart. It's called known as a vibration. This movement is referred to as vibration. There are different types of vibrations. There is something called a symmetrical vibration and asymmetrical vibration. I just have to do some demonstration here because I cannot do it on the screen. So let me show you how the various vibrations occur. Let me know whether it's whether you can see this. Look at this. There can be like various different types of vibrations. This is one type of vibration. you have like, this is 2 pens in my hand. So imagine this is the, let me just move this a bit. The 2 atoms, imagine this is the 2 atoms. So you have 2 atoms vibrating this way symmetrically, right? This is symmetrical vibration, right? That means equal vibration. And then there's another type of vibration is that one vibrates more than the other. That's called the asymmetrical vibration. So both can vibrate like this, right? Symmetrically, equal amount, or one can vibrate more than the other. One vibrates less, the other one vibrates more, right? And then you have the other one vibrating more than this one. So this is different types of vibrations. You have the symmetrical vibration and asymmetrical vibration, right? So this is the nature of the bond. And also there can be bending, right? The bond can bend like this, right? So there are different bending modes. You have symmetrical bending like this. So imagine this is a bond, right? So you have like this, the symmetrical bending, equal bending, and one bends more than the other one. That's called asymmetrical bending, right? Symmetrical bending, asymmetrical bending. So this can happen in a bond. So you can, bond can stretch like this, stretching vibration, and that can be symmetrical stretching like this, or asymmetrical stretching. Is asymmetrical stretching, or a bond can bend like this, symmetrical bending, or it can be asymmetrical bending. One can bend more than the other, right? And the third type of vibration is that while it's bending, it will stretch like this. It's difficult for me to, demonstrate this. While bending this way, right? While bending, it stretches. So that is known as what you call mixed vibration. While bending is stretching. While bending is stretching. So there are different types of this type of vibration. While bending is stretching is known as mixed vibration. That can be like symmetrical bending and symmetrical stretching, and asymmetrical bending and asymmetrical stretching. So there are different types of stretching and bending vibrations, right? So this is the nature of any bond. It can be vibrations, like all are vibrations, because the nuclei come close to the shared electron pair. So after some time, because the nuclei is very closer, they repel away from it, and then again they come closer. This is known as vibration. So there can be stretching vibrations and bending vibrations, as I explained. There can be symmetrical stretching, asymmetrical stretching, symmetrical bending, and asymmetrical bending, right? So all these vibration has a certain amount of frequency, right? There are a certain amount of frequency. Right? They produce certain amount of frequency. And all these frequencies of the stretching, bending, symmetrical, asymmetrical, and mixed vibrations, all these types of vibrations, their frequency coincides with the frequency of the visible light. All these vibrations, different modes of vibrations, their vibrations coincides with the IR radiation, of the visible light, the IR radiation, infrared radiation. So infrared radiation is a larger frequency, which is from wave number wise is between 500 to 4,500 per centimeter. That's wave number. Wave number, as you know, it's reciprocal of the wavelength, 1 upon lambda. So it's a huge frequency range, right? So this all bonds, therefore, have different types of stretching and bending modes, and all of them the frequency during the stretching and bending and all vibrations fall within the IR radiation. So the energy transitions responsible for IR's spectrum is concerned with the vibrations of molecules. The atoms in a covalent bond is held by the pair of electrons attracted to the both nuclei. The nuclei can vibrate backwards and forwards, towards and away from each other. Stretch is a vibration occurring along the line of the bond. Bend is a vibration that does not occur along the line of the bond. Diatomic molecule can undergo only a stretching vibration. Polyatomic molecules can undergo symmetrical and asymmetrical stretches and bends. Each stretching and bending vibration of a molecule occurs at a characteristic frequency. When a compound is bombarded with the radiation of frequency, it exactly matches the frequency of one of its vibrations. The molecule will absorb energy, thus resulting molecule to stretch and bend a bit more. That means for certain bonds, each and every bond will have its unique stretching and vibrating modes. So if you give that same frequency, for example, if say C double bond O has a frequency given, say, frequency called X. So if you give the same X frequency externally, what happens? It will absorb that X frequency, because it will absorb the frequency and it will even stretch and bend even more, right? So let's draw the different types of stretching and bending vibration. You can copy this. This is stretching vibration, bending vibrations, and I'll draw the mixed vibration afterwards. So this is stretching vibration. This is symmetrical stretching. One is more than the other. Asymmetrical stretching. Bending happens in polyatomic molecules. I have drawn the atom like the bond like a spring. So this is symmetrical bending, and got the one bends more than the other. This is asymmetrical bending. Then you got the mixed vibration. I'm sorry at the space. I'll try to draw it here. Mixed vibrations. This is like this. At the same time, stretching and bending. So symmetrical, asymmetrical, stretching and bending. Symmetrical, asymmetrical, stretching and bending. Please copy these 5 different modes. Let me know once you're done. So let's see how the infrared spectrum is produced. Now, what happens here in infrared spectrum is that now, as you know, each stretching, so the symmetrical, asymmetrical, bending, symmetrical, asymmetrical, and it has a mixed vibration. Each of these will have a unique frequency, right? Each will have a unique frequency. So I said all this frequency of different vibrations fall within the infrared range, infrared frequency range. So in infrared spectrophotometer, what we do is we give IR radiation to the molecule. As I mentioned before, when each molecule and each bond will have its unique frequency, what it does is it absorbs that particular frequency from the external IR frequency. Right, so I'm giving the entire IR range, which is from 500 per centimeter to 4,500, and what happens is that each bond will have a unique, frequency. So that particular frequency will be absorbed from the external IR frequency. Right, this is what exactly happens. So when based on the absorptions of the IR, we can easily identify the presence of different bonds in the molecule. This is very useful to identify the functional groups, like the OH bond, the C double bond, O. So those groups can be easily identified from this method, right? So in a spectrophotometer, the IR spectrophotometer, the spectrum is produced as dips. So when there is no absorbance, what happens is that everything, all the IR radiation is emitted. If there's no absorption, that means there's no molecule. If there's any absorption, then there will be a absorption of the IR radiation. So what is transmitted will be much less, right? So in IR spectrophotometer, IR radiation is passed through the test sample. The molecule absorbs IR radiation, which has a wavelength longer than the visible light, which is just below the red region of the visible light. Infra is Latin for below or next to. When the molecule absorbs radiation, the bonds vibrate more energetically. The frequencies absorbed for these vibrations are dependent on the bonds. Different bonds absorb different frequencies, as it is characteristic for a particular bond. Therefore, IR absorptions can be used to identify bonds and therefore functional groups of a molecule. Right? Detector of the spectrophotometer produces IR spectrum on a chart recorder. How much of a particular frequency get through the compound is measured as a percentage transmittance. A transmittance means what is given out. That means you give IR radiation, it absorbs part of it and gives out the rest. So if transmittance is 100%, that means nothing is absorbed. If transmittance say 25%, that means 75% is absorbed, right? So transmittance of 100% means that all the frequency is passed straight through the compound without any absorption. Transmittance